Here's problem number 14 from your lesson 7.4 homework, and we're graphing this rational function, so let's get right into it. The first thing we'll do is look for X-intercepts, or real zeros, and that is when we let the numerator equal 0 and solve. Well, there is no variable in the numerator, and obviously 5 will never become 0, so we do not have any x-intercepts. This graph is not going to cross the x-axis at all. And I notice that this rational function is already factored, so that's good, and there's nothing obviously that we can cancel between the numerator and the denominator. So no x-intercepts. All right, so now let's take a look for asymptotes. We'll start with vertical. Do we have a vertical asymptote? Those are numbers that make the denominator 0 if we plug those numbers in for x, and it looks like we have 2. 1, if we let x be 1, we'll have 0 times 5, which is 0. If we let x be negative 4, we'll have 0 times negative 5, which is also 0. So each of these numbers causes the denominator to become 0 when we substitute them in for x. So that means we have 2 vertical asymptotes. So here's x equals 1. And here's x equals negative 4. All right, so now let's check for horizontal asymptotes. Here's where we compare the degrees. The degree of the numerator is actually 0. The degree of the denominator is 2. If you were to FOIL this, you would end up with x squared as the first term. So that means the denominator degree is 2. So whenever the denominator degree is larger than the numerator, remember that means we do have a horizontal asymptote, and it's the line y equals 0, otherwise known as the x-axis. I'm going to draw a dotted line on top of the x-axis just as a reminder that that's another asymptote line that I'm going to follow or trace along with my graph. Okay, and then while I'm at it, at this stop in my process, I'm going to look for a hole in the graph. A hole would be a number that causes both numerator and denominator to become 0. Well, since we don't have a variable, we already said this, there's no variable in the numerator, there's no way that we could ever make this become 0. So there is no hole that needs to be graphed. Okay, so we've taken care of the first 2 steps, and now the final step will be to come up with some points, inputs and outputs. And basically we want to know what happens to the left of x equals negative 4. So let's just pick a number like negative 5. Okay, let's just input negative 5 into this function and see what we get as the output, and we'll have an ordered pair that we can graph. So 5 over negative 5 minus 1 times negative 5 plus 4. And when we simplify this, we get 5 over, this is going to be negative 6 times negative 1. And that multiplied together makes positive 6. So it's 5 over 6, or 5/6. Okay, so that's good information. We'll go to negative 5 and then not quite to 1, just short of the positive 1 mark. 1 would be 6 over 6. And this is similar to the one we did in class in your notes. I'm pretty much going to trace the asymptote lines the rest of the way. So I'm going to say that going through this point, we're going to go up the vertical asymptote forever. We're going to approach but never touch. And then we're going to go to negative infinity along the horizontal asymptote forever. Approach but never touch. And so that's one of the 3 pieces of this graph. Okay, The other piece will fall in between these two vertical asymptotes. So let's pick some numbers right in between. And I usually like to start, I mean, you can start anywhere you want, but I'm going to start right in the middle, okay? Right in the middle of +1 and -4. So that should be 1, 2, 3, 4. There's 5 marks altogether. So if I go 2.5 marks, I'm actually at x is -1.5. So you see what I did there? I just counted up the total of marks, and then I split the difference. I'm just going to test right in between and see where that point is. So -1.5 is my input. So you might want your calculator for this one. Let's see what we get as an output. All right, obviously numerator doesn't change. So -1.5 minus 1 is -2.5. And then -1.5 plus 4 is +2.5. So I just went ahead and paused for a second so I could pull up my calculator, and you might want to double check and see if you get the same thing. When I did 5 divided by -2.5 times +2.5, I got -0.8 as the output. Okay, so for -1.5, here's -1, here's -1.5. I'm going to go not quite to -1. Okay, and now I'm just going to see what happens on either side of that point. Does it happen to go up higher before it comes down? So let's choose, let's do -3. Okay, let's do see what comes out when we let the input be -3. Alright, so I'm just showing it like this. -3 plus 4. So this is -4. This is +1. And we get 5 over -4. That's -5/4, or it's -1 1/4. Okay, so it's a little bit lower than this dot we have here. So 1, 2, 3, -1 1/4. All right, so let's try 0. Okay, if we try 0 as an input, looks like we're going to get the same thing. So this has some symmetry. -1 times 4, so we get the same result. So by choosing the point that's right in between these two vertical asymptotes, we basically have symmetry at that point. This is going to be the vertex of a parabola that opens upside down. So 0, -1 1/4. And so here's our parabola. We'll follow this to -infinity going that way, and -infinity going that way. Okay, so 2 down, 1 to go. And I'm guessing that this is going to be the final piece, and it's really just going to be this shape flipped the other direction. It's typically what happens in these graphs, but we'll go ahead and know exactly what point to draw through. Let's choose 2 as an input. Okay, we want to find out what happens to the right of x equals 1. So I'm going to input 2 into my function. All right, so let's set this up. 2 minus 1, 2 plus 4. Looks like we're going to get 5, 6. So 2 minus 1 is 1 times 6. I'll erase this. 1 times 6, so we get 5, 6. All right, so for 2, just up a little higher, and I'm just going to draw through that point and trace alongside the asymptotes for the rest of the graph. We'll approach forever as x approaches positive infinity, and also as f of x approaches positive infinity. Okay, so I think we've got everything. No hole to go back and plug in, And that looks like our final graph. So that is number 14. And let me know if you have any questions.